Welcome to this explainer. Today, we're diving straight into the complex, invisible physics of nuclear fission. We're going to take some pretty dense subatomic mechanics and translate them into a highly visual story of opposing forces. It's a microscopic battle that literally powers cities and reshapes elements, and we're going to make perfect sense of it right now.
Here is our roadmap for today. We'll kick things off with a subatomic tug-of-war. Look at how the nucleus actually changes shape to split. Talk about crossing the fission barrier. Explore the ultimate quest for stability, and finally, figure out exactly which atoms will split.
All right, part 1, the subatomic tug-of-war. Everything we're talking about today really starts with this fundamental conflict happening deep inside the nucleus.
You know, fission isn't just some random chaotic explosion. It's actually a highly structured tug-of-war between two fiercely competing physical forces. On one side, you have surface binding energy. This acts kind of like a shield. It actively opposes deformation and just wants to keep the nucleus tight, compact, and stable. But on the exact opposite side, you've got Coulomb binding energy. Because Coulomb energy is fundamentally repulsive, it enhances deformation. It's actively trying to tear the nucleus apart. Ultimately, if the Coulomb energy overpowers the surface energy, the atom breaks.
Moving on to part 2, changing shape to split. Let's see how this physical evolution unfolds when the nucleus actually starts to give way under all that pressure.
As that repulsive Coulomb energy starts to win out, specifically because the atom acquires extra energy, the atom goes through a really distinct stretching process. It doesn't just shatter instantly. First, it elongates from a sphere, distorting into an ellipsoid. Then, as the internal forces push harder and harder, it grows into a dumbbell shape with a very noticeable neck right in the middle. And finally, when that neck just can't hold on anymore, it snaps, and the atom splits.
Now, what we're looking at here maps that exact physical transformation perfectly along the atom's potential energy curve. Notice how the atom starts off as a tight sphere, but as it acquires energy and moves along the separation path, it stretches out into that ellipsoid, thins into the dumbbell, and finally breaks into two totally separate fragments. Every single shift in its geometry is dictated by that invisible tug-of-war we just talked about.
That brings us to part 3, crossing the fission barrier. Just like climbing a mountain, the atom needs a very specific amount of energy to reach the peak before it can roll down the other side and separate. So we have to talk about critical energy. Think of this as the absolute minimum push required to force the nucleus up that hill. The compound nucleus needs an adequate energy injection, excitation energy, to move from its initial resting state all the way to the top of the barrier. Without meeting this critical energy requirement, the mountain just can't be conquered, and fission is absolutely not going to happen.
But once the atom actually reaches this scission point, which is marked as stage B on the energy curve, there is absolutely no turning back. It is the absolute peak. At this exact stage, the fragments are right at their short-range touching distance. Once they are left free at this peak, the repulsive Coulomb forces take total control. They heavily repel each other, pushing the fragments all the way down the other side of the curve toward complete separation. Basically, reaching the scission point guarantees the split.
All right, part 4, the quest for stability. Now, you might be wondering, why on earth does the atom undergo this violent tearing process in the first place?
I mean, does this violent split actually make the atom more stable? It sounds totally counterintuitive, right? Disintegration and splitting usually sound like chaos, but the universe always favors a state of higher stability. So let's look at the math.
Let's track a real-world scenario to see how this plays out. Imagine a neutron strikes a target nucleus of uranium-235. It absorbs that neutron and briefly, very briefly, becomes a highly unstable compound nucleus, uranium-236. Because of that extreme instability, it violently splits into two distinct fragments, barium-141 and krypton-92. Plus, it sends 3 additional neutrons flying off.
And the mathematical proof is right here in the binding energy per nucleon. The original compound nucleus, uranium-236, sits at roughly 7.58 MeV. But check out the fragments. Barium jumps up to 8.32, and krypton goes even higher, to 8.51. In nuclear physics, a higher binding energy per nucleon means a tighter, much more stable atom. So fission isn't just destruction for the sake of it. It leaves the resulting products in a far more stable state and releases a massive amount of energy doing it. That massive release, that is exactly what boils the water in nuclear reactors to power our cities.
Okay, moving to our final section. Which atoms will split? Because not all atoms are built the same,
and some are way harder to push over that mountain than others.
This introduces us to a very special category: fissile nuclides. These are target nuclides that can essentially fission no matter how incredibly small the incoming neutron's energy is. The binding energy they get just from absorbing the neutron is, all by itself, enough to exceed the critical energy required to split. Because of this, their required threshold energy is zero. They are literally primed and ready to go.
So the obvious question is, which specific isotopes are actually fissile? Let's check out the data and see who the prime candidates are.
Take a close look at the threshold energy column here. Thorium-232 and uranium-238 have positive threshold energies. That means fission for them is a threshold reaction. They require a hard kinetic push from a neutron. But look at uranium-233, uranium-235, and plutonium-239. Their critical energy is low enough that their threshold energy is exactly zero.
That magical 0.0 threshold energy is an absolute game changer. It means that, however tiny the neutron energy might be, the compound nucleus formed will automatically exceed the critical energy needed to undergo fission. It's an incredibly powerful property that's inherent to only a very select few materials in our universe.
Now, before we wrap up, there's a golden rule we absolutely have to remember. The fissile or non-fissile attribute is given to the target nuclide and not to the compound nucleus. We label uranium-235 as fissile because it's the original target. We do not apply that label to the temporary uranium-236 it briefly turns into. Getting this right is absolutely crucial when you're dealing with the real-world math of reactor physics.
So, we've seen how a subatomic tug-of-war literally tears the core apart just to find mathematical stability. It leaves us with a really fascinating paradox to chew on long after this explainer ends. If ultimate stability sometimes requires complete and utter destruction, what other invisible forces are quietly shaping the universe right beneath our noses? Thank you for exploring the mechanics of fission with me today. Keep asking questions and keep looking deeper into the data.